Hello, I welcome you all in this course on steam and gas power systems. Today we will start with the nozzles and diffusers. First of all, we will take up type of nozzles and diffusers, then equation of continuity, sonic velocity and Mach number in case of nozzles and diffusers, then momentum equation. Now let us start with the nozzle. Nozzle is a passage of varying cross section. Nozzle is a passage of varying cross section. It may be converging or diverging, or the varying cross section may be converging and diverging as well. So, it is a passage of varying cross section where pressure energy is converted into kinetic energy. All of us know the equation P by rho plus C square by 2 plus Gz is equal to constant. So, in a nozzle, at the expense of pressure energy, kinetic energy is attained, and this high velocity jet which is emerging from the nozzle is used for variety of the purposes. So, regarding the uses of the nozzle, first of all, it is used in steam turbines, hydro turbine or water turbine, and gas turbines. Now, the purpose of the nozzle is to convert pressure energy into the kinetic energy, and mass flow rate remains constant throughout the passage of the nozzle. The mass flow rate of the fluid remains constant, and this high velocity jet emerging from the nozzle hits the turbine blades and causes turbine rotor to rotate in a particular direction, and that is how high grade energy or the work is produced in a turbine. Now, another use of nozzle is jet engine. In jet engine, for the purpose of creating thrust, the nozzles are used. Rockets, then public use fountains, then flow measurement. Nozzles are also used for flow measurement in a passage. In addition to this, water injection in a boiler, or for the removal of air in condenser, steam ejector in condenser. There are a few examples. There are many other uses of nozzles which I cannot list here. There are three types of nozzles. If we go by the classification of the nozzles by the cross section of the nozzles, there are three types of nozzles. One is convergent nozzle, where the cross section area of the nozzle decreases. This is the passage of the nozzle, this is the wall of the nozzle. So, flow is taking place in this direction. Cross section area of the passage keeps on decreasing. This is known as converging type of nozzle. Another type of nozzle is diverging nozzle, where cross section area of the nozzle increases, and at the same time the velocity of the fluid also increases in a particular condition. So, these type of nozzles are known as diverging nozzles. If you connect them, then it becomes convergent and divergent nozzle. And this is throat area. In throat area, there is no change in cross section. So, nozzle has three parts: inlet and outlet, converging part, diverging part, and a throat which in the throat there is no change in the cross section area of the nozzle. Now, another part is diffuser. Now, in diffusers, kinetic energy is converted into the pressure energy. The function of diffuser is reverse of the function of nozzle. It can be axial flow diffuser like this, or it can be radial flow diffuser also. In radial flow diffuser, the best example is centrifugal pump, where kinetic energy of the fluid is converted into the pressure energy. So, that is one of the main application of the diffuser. There are many other applications, but centrifugal pump, the kinetic energy is imparted to the fluid and subsequently this kinetic energy is converted into the pressure energy with the help of a diffuser. Now, we will start with the continuity equation. Let us take continuity equation of a flow through a nozzle. This is m is equal to rho a v, v is the velocity, or here we are denoting v by c. So, c is the velocity, and doing partial differentiation, it is going to be del m by m is equal to del rho by rho plus del a by a plus del c by c, right. Now, mass flow rate is remaining constant throughout the passage. So, this is 0. Now, we are having only del rho by rho plus del a by a plus del c by c is equal to 0, right. So, while flowing through a nozzle passage, suppose air or steam is flowing through the nozzle, area will vary, velocity will vary and density will also vary. Or we can say by virtue of variation and in density and the velocity, area of the cross section area of the nozzle will vary. However, in the case of liquids, in liquids change in density with the pressure is insignificant. So, this can be neglected. So, we can write del A by A plus del C by C is equal to 0, or del C by C is equal to minus del A by A, right. It means at the expense of pressure, when the velocity of the fluid is increasing, the cross section area of the passage will keep on decreasing, or it is going to be in this shape even at very, very high velocity. Now, let us do first law analysis of the flow of fluid through the nozzle. Let us take a passage or of varying cross section. The walls are rigid, there is no movement in the wall of the nozzle. Fluid is flowing in this direction. This is plane 1, this is inlet, this is plane 2 at outlet. And let us say this is control volume on which our study is focused, very close to the wall, right. And if we write first law equation for flow, that is del P by rho plus CdC plus GdZ is equal to 0, right. Or no, this is not sorry, now this is DH, not del P by rho, this is DH. So, DH plus CdC plus GdZ is equal to 0, or in terms of 1 and 2, H1 minus H2 plus C1 square minus C2 square by 2 plus here GdZ, because it is a horizontal direction. So, there is no change in the potential energy. So, this can be taken as 0 is equal to 0, or we can write C2 square minus C1 square by 2 is equal to H1 minus H2. If you want to write in differential form, then it is DH is equal to minus CdC. Now, if the C1 is 0, C1 is not 0, if you compare the value of C2 and C1, C2 is much larger than C1, or outlet velocity of the nozzle is much larger than the inlet velocity, and it is often neglected because if you consider the inlet velocity, it is not going to make much difference. So, often it is neglected. So, we can always find the C2 square is equal to 2 H1 minus H2, or exit velocity from the nozzle is under root 2 H1 minus H2. But we should remember that enthalpies are given in kilojoules. So, this kilojoule has to be converted into the joules while calculating the exit velocity. So, C2 is going to be under root 2 into 1000 H1 minus H2, and it is going to be under root 2000 H1 minus H2. We have multiplied H1 minus H2 by 1000 just to convert kilojoules per kg to joules per kg, and here we get 44.72 under root H1 minus H2. This is regarding the flow of the fluid. Suppose there is a gas nozzle. The working fluid in a nozzle is gas or air. In that case, C2 can also be taken as under root 2 Cp T1 minus T2. This is the change in enthalpy of the gas. Or if you want to further simplify it, then 2 Cp T1 1 minus T2 by T1. Here you can use the ideal gas relation, T2 by T1 is equal to P2 by P1 raised to power gamma minus 1 over gamma. So, C2 is going to be equal to under root 2 Cp T1 1 minus P2 by P1 raised to power gamma minus over gamma. Because pressure drop in nozzle is often expressed in the terms of ratio of downstream pressure and upstream pressure, right. So, this can be expression for the velocity of air or gas coming out of the nozzle. Now, after this we will take up the momentum equation for the flow inside a nozzle. Let us take a generalized case where there is a convergent divergent nozzle. And let us take a thin section out of this of distance delta x. Now, if we do the force balance on this section, in this direction the force is pressure into area. Whatever pressure is existing on this side multiplied by the area. Now, force exerted on this from this side is P plus delta P, A plus del A, whatever it is, because normally in the in this direction there is a fall in pressure, but to have a generalized equation we have taken P plus delta P exerted on this direction, right. Now, this is the nozzle wall, and pressure of the fluid is outside, pressure is greater than the pressure outside this nozzle. This is wall. So, for whatever analysis we have done, we have considered flow through nozzle is adiabatic flow. If you remember the equation, this equation dH plus CdC plus GdZ is equal to 0. Here also we have considered that the flow through nozzle is adiabatic, and because walls are rigid, so there is no work. So, del Q is equal to 0 and del W is also 0. Considering this only, we have derived the equation C2 is equal to under root 2 H1 minus H2, right. Now, here when we are doing the force analysis, force is also being exerted on the wall of the nozzle. So, force is also being exerted on the wall of the nozzle by virtue of pressure of fluid inside this nozzle, and reaction will work in this direction. Reaction will work on this element in this direction. If you take from the vertical, this is phi, and this is the nozzle diverging angle is also phi, because nozzle is a diverging passage. This is a diverging passage, and this angle is phi. So when we take pressure from normal to pressure is normal to this surface, so this angle is going to be phi, right. Now second thing is, this is a ring of, this is in fact a ring around the periphery of the nozzle of thickness dx. So if it is a ring of thickness dx, if you take a small element on this ring which is exerting delta theta at the center, a small element on the ring which is exerting delta theta on the center, right. On the entire ring, suppose it is, so part of the ring is exerting delta theta on the center. If I want to have area of this element, it is going to be r delta theta multiplied by delta x, right. Now this area is then again, now we have found this area, now projection of this area in this direction. So projection of this area in this direction, this is delta phi, is going to be sec phi. Now force is exerted on this, and reaction of this force is in this direction, and component of force in this direction is going to be, this is phi, component of this force in this direction is going to be, I will expand this diagram, it is something like this. Force is working in this direction, reaction force, this is phi, and component of force in this direction. So component of this force in this direction is going to be sin phi, P sin phi. This is area and this is P sin phi. So this will give you the net force working in this direction in this passage due to pressure. Now the net force is PA, this pressure into area, right, minus P plus delta P, A plus delta A, plus this force. Now this force R delta theta del x sec phi and sin phi is tan phi, P tan phi, right. If we integrate this, integrate this 0 to 2 pi, this will become 2 pi r delta x tan phi multiplied by P, right. Now delta x tan phi is delta r. So it is going to be 2 pi r delta r multiplied by P, and 2 pi r delta r is nothing but delta A. And this force is also working in this direction. So we will also add P del A. Now the third force we will consider the force of friction, which is opposing the movement of the flow of in this direction. So that is going to be, let us say, minus delta, we do not know this force, that is going to be minus delta F. So that is the net force working on this element, right. Now this net force, we will simplify this equation, PA minus P delta A minus A delta P minus delta P delta A plus P delta A minus delta F, right. Now here we can cancel out some terms, some of the terms, that is PA, this will be cancelled out, P delta A will be cancelled out. Now this we can consider to be 0 because delta P is very infinitesimal, this is also infinitesimal, so their product will tend to 0. So we are neglecting this term. So, net force we are getting in the direction of the flow is minus A delta P minus delta F. Now, this force is mass into acceleration, mass of the fluid in this and acceleration of this. So, mass of the fluid is going to be A delta x by specific volume. This is volume of this element divided by this specific volume multiplied by acceleration. Acceleration is delta c by delta t. Okay, here there is an unknown term delta t. So, delta t c is del x by del t. So, del t is always del x by c. So, we will replace this del t by del x by c. Now, here we can again cancel out this, right, and further simplification will give us the equation C del C is equal to minus V del P minus V by A del F. Just multiply by V, divide by A, we can further simplify this equation like this, right. Now, again we have this term. Work in the friction per kg of fluid, right. Work in the friction per kg, because here we are considering friction. So, work in the friction per kg of the fluid, work is F in force into velocity, right. So, friction here force is delta F, velocity is C, divide per kg, per unit mass. So, in order to find mass of the fluid, we will divide it by area, velocity divided by specific volume. So, this is work and this is mass of the fluid which is flowing. We can further simplify it as C del F, and the C and C will be cancelled out, right. So, we will be getting V del F by A. This is friction per unit mass flow rate, and this means this is friction per unit mass flow rate, and this is denoted by minus, this is denoted by Wf. So, we can further rewrite this equation as C delta C or C delta C, not C dot delta C, C delta C is equal to minus V del P minus del Wf. If the change is tending to 0, then this equation can be written as C dC is equal to minus V dP minus dWf, right. If you remember that equation, C dC is equal to minus dH, energy equation, right. In that case, dH is going to be equal to V dP plus dWf, right. Or we can write C2 square minus C1 square by 2 is equal to integral P2 to P1. I am not writing 1 to 2, I am writing 2 to 1. So, it is V dP minus dWf, right. So, this is the momentum equation for the flow of fluid inside a nozzle. If the friction is in ideal flow, when the friction is 0, we can always consider this equation as the momentum equation for the flow inside a nozzle. This is all for today. Thank you very much.